ওখানে তো তার আগে তো হয়ে গেছে বলে, তাই না?
এক্স্যাক্টলি মনে নেই।
তার আগে তো আচ্ছা, এখানে যে জেডি আছে কিন্তু স্মল
কি আছে?
মানে এখানে জেডি আছে মানে এই জায়গাটা মানে এটাই আমার অন অফ করতে হবে, এটাই তো
স্টুডেন্ট।
হ্যাঁ, সেটা ঠিক আছে।
লাস্টে স্টুডেন্ট কথা বলি।
আচ্ছা, কিন্তু এটা এখন আমার দিস belong to me, that means I'm on. এটা তো এইদিকেই তো, ডান দিকে or anyone, okay, all right. Good morning everybody, can you hear me?
Yeah.
Okay, thank you very much. All right, so maybe we will just wait for another minute or so as people are joining. By the way, any question that you might have had after the lecture? Okay. Now, well, just to summarize in a few sentences what we did last time, which is that we talked that we have to approach it in a little bit formal and abstract way, because we are not talking about any particular computer or any particular algorithm, let us say. So we want to have an abstract view of what computation is, and then we will discover its boundary. In order to do this in an abstract manner, we have to go about it in a formal way. So for that we discussed the language of propositional logic and then first order logic, which will be our main concern. And we saw that how at least the natural numbers and arithmetic over natural numbers, that could be formalized through actions and all. All right. And now, having talked about the approach to the abstract models, then we will talk about actual abstract models today. And what basically we want to do is that what can be done with, let us say that now I'm saying first order logic. Naturally, if there are limits to first order logic, those limits will also apply to any system you make out of first order logic, and then that system may have its own limitations. We will talk about it. Apparently, we can do basic arithmetic with arbitrarily large numbers. This we have seen. The question is, can we compute any functions over natural numbers? Can we prove all truths about arithmetic and natural numbers? The answer, unfortunately, is no. That means we can do some things, but there are other things we cannot do. You might ask that what is it that we cannot do on natural numbers? Well, it is difficult to tell you specifics, but there are theorems which prove that this is not possible. We'll discuss that. And for this, we will revisit semantics and introduce the notion of decidability. Okay? Semantics, we have already talked about it. This is the idea of truth. As you remember, the first order logic, there is a syntax part. And the syntax gives you through a grammar, etc., whatever it gives you just strings of symbols. Whereas there is nothing more, nothing less than that. So an interpretation of first order language assigns a denotation to each non-logical symbols. That means now we are coming to what does it all mean. So we have to give it some meaning. The same thing may mean different things depending on what kind of denotation you are putting in it. And what do we mean by denotation? That each non-logical symbol in that language denotes something, okay, that we will see. And it also determines the domain of discourse that specifies the range of the quantifiers. If I say variable for all x, now what do you mean by for all x? For all x in a certain set, and that set will come from the domain of discourse. The result is that each term is assigned an object that it represents. Each predicate is assigned a property of objects, and each sentence is assigned a truth value. In this way, an interpretation provides semantic meaning to the terms, the predicates and formulas of the language. The question is whether there is an effective method to do this. Naturally, whatever we want to do it mechanically. So for that, there has to be an effective method. Now we come to this notion of decidability. Say in propositional logic, some formulas are tautologies. Say P or not P. That is a tautology. That is always true. Now this truth is not dependent on what kind of denotation you are doing. That means what kind of system you are saying. Assuming that the system is consistent. So they have the property of being true in all interpretations. They are called tautologies. So there is a procedure which can be used to tell whether a formula is a tautology in propositional calculus. This procedure is the truth table method. We all know this. What about first order logic? A formula of FOL that is true under all interpretation is said to be valid. Okay. Just as I said, P or not P is true in every interpretation. Similarly, for all x, Px or non-Px is also valid as a first order formula, and this is valid in all interpretations. Now, we can't use truth table, but we cannot use truth table to tell us whether a formula of FOL is valid or not. Simply because this variable domain may be infinite. That is one reason. There are maybe other reasons. For example, when I say for all x px, actually it stands for so many propositions. PA, PB, PC, PD, etc. Assuming A, B, C, D, these are all constants in the domain. Okay, so when I say for all px, for all x px, I am implying that PA, I am also implying PB, I am also implying PC, I am also implying PD, and so on. Which means, sorry, that one formula is actually standing for so many propositions. When I put some, say, constant A for X, PA, we might call it a proposition, right? Now, so that is why we cannot use truth table any longer. Is there any other procedure that we can use that will be guaranteed to tell us in a finite amount of time when a FOL formula is or is not valid? Well, here also the answer is no. That means first order logic is for this reason said to be undecidable. Okay. We cannot check, there is no guaranteed, just as with truth table, we had a guaranteed way of saying whether something is a tautology. But in first order logic, there is no such thing. So here we distinguish two concepts. One is provability, the other is logical validity. Each logical system comes with both a syntactic component, as we said, those are the strings of symbols, which among other things determines the notion of provability. Now from these strings of symbols, what other strings, so say some strings meaning formula, of course, well-formed formula, can be proven. So that is the notion of provability and the semantic component. Semantic components which determines the logical validity. The logical valid formulas of a system are sometimes called the theorems of the system, especially in the context of first order logic, where Gödel's has given a completeness theorem which establishes the equivalence of semantic and syntactic consequence, meaning that in semantically if something is true, you can syntactically derive it. But it is not syntactically complete. I am just coming to that. So what it means is that if something is indeed logically valid, that means semantically it is supposed to be true, then we should be able to prove it. That is what Gödel's completeness theorem tells us. What is completeness? We have talked about it, but just to revise, a set of axioms is syntactically or negation complete if for any statement in the axioms language, that statement or its negation is provable from the axioms. That means if it is provable, that means if any such statement or its negation is provable, of course the statement has to be well formed. In that case, we call it complete, syntactically complete. And semantic completeness, which means that the set of axiom proves all the semantic tautologies of the given language. In his completeness theorem, Gödel proved that first order logic is semantically complete. Unfortunately, as I said earlier, that can we prove everything? That means there we meant it syntactically. Unfortunately, it is syntactically not complete in the sense that, hello? Anybody? Okay.
Yes, sir, I can hear you.
Okay, thank you. So that is what. And then there is a good, famous one or two, you might say. One, the second and third is a sort of extension of the second. That is a Gödel's incompleteness theorem. These two are absolutely famous theorems. The incompleteness theorem is more talked about and more famous than the completeness theorem. I'll just talk about it and then maybe explain it a little more. The first incompleteness theorem states that no consistent system of axioms whose theorem can be listed by an effective procedure, that is an algorithm, is capable of proving all truths about the arithmetic of natural numbers. Okay. This is being put in the context of natural numbers here, but is also provable as a consequence, it is also provable for other FOL systems. What is it? What is it saying? That if we have an effective procedure or algorithm, let us say, which keeps on generating all the theorems, okay, which are provable. Unfortunately, there is no system of axioms which allow you to generate such theorems which are capable of proving all the truths about the arithmetic of natural numbers. For any such consistent formal system, there will always be statements about natural numbers, that means statements which you can form syntactically that are true, but that are unprovable within the system. And the second incompleteness theorem, an extension of the first incompleteness theorem, that is, first theorem is the consistent and the completeness part. The first shows that the system cannot demonstrate its own consistency. Okay? We will not have much of this thing to discuss all the ramifications of this. Maybe we will just touch Gödel's incompleteness theorem in this thing, just to give you some idea. But let me take 5 minutes to tell you what this really means. This really implies that you may have a formal system, where a first order system, where you have put the axioms which you think are all right, but this is not all there is. Okay, that means all the truth there is. And more startingly, that there will be statements which can neither be proved nor be disproved. Now think about it for a second. What does it mean that you can? There are statements which can neither be proved nor be disproved. Well, in that case, you can add it as an axiom to the system, either that statement or its negation. You can add it as an axiom because that is not going to lead to any inconsistency. And you can add and then add some more and keep on adding a finite number of times. So you may introduce 50 more axioms or 5 million more axioms. Still, it is going to be incomplete. Okay. Now, I'll just give you. I mean, I stopped here and went off in this tangential direction just to give an idea that why theory of computation is so important. You may have heard that recently, in the last, I would say 2-3 years, maybe, there is again another general this thing about AI, artificial intelligence, and people make all kinds of statements. I mean, many of them are, of course, not computer scientists at all, but some of them, unfortunately, are, and they make claims, etc., which are patently false. For example, I do not know whether you have heard about it, that there are some people who talk about technological singularity. What is this technological singularity? The notion is that these by Moore's law, our machines are becoming more and more powerful and bigger in terms of memory space and all that, all the time, in an exponential fashion. So very soon they will be much, much bigger than, first it will be bigger than individual human brains, and then it will be, then the cloud will be bigger than all brains of all human beings put together. And then through, I mean, these futurologists, let us say, they think that you can sort of upload your brain into the cloud and then you become immortal. And this whole thing will be controlled by a so-called AI-based system. AI will control all human beings, and so then you are free of all physical limitations. Now, if you know or understand what this about theory of computation, you know that this is nonsense. Why? Simply because you will never have any AI system which is good enough for this purpose. I think maybe you have learned. I mean, you have gone through the AI course by now. Is it? Have you? I'm asking a question. Somebody? Have you done AI?
We are doing it this semester.
Oh, you are doing it this semester. Okay. Then you will find that it starts with maybe heuristic search, etc., etc., and then finally it comes to say theorem proving first order calculus. Again, you will sort of do over there when you do theorem proving. So in the theorem proving, you may either do resolution based theorem proving or forward chaining, etc., backward chaining, etc., etc. Once again, using the first order this thing. That is incomplete. What can you axioms put in such a super system, global super system? You cannot. So this is obvious. So this is so that human beings can depend on AI for all aspects of their life. This is nonsense. You cannot do it. So these are things, and you would know that they are nonsense if you know the say theory of computation. Okay. Similarly, there are other listings of this incompleteness theorem. For example, it. I mean, if you see the last line of the slide, it says that the second incompleteness theorem is an extension of the first, shows that the system cannot demonstrate its own consistency. Not only that, it cannot demonstrate its own consistency. If you put some metasystemic questions, it will fail. For example, I ask about an axiom, is it useful? And things like, is it good? Is it complete? All these metasystemic questions, as you put in, it is not going to be able to answer. Okay, that is simple. So now, as I said, that you can add new axioms and have another system, a bigger system. So there may be some important metasystemic issues which you want resolved in a certain way, and you put in those actions that you can do, but you cannot do it indefinitely. Now, which metasystemic questions are important to incorporate, that is again a meta thing, which again is unknown. Okay. Anyway, now let us come back to the to this course. So what I am trying to say is that this theory of computation is not just lots of mathematics. Although, I mean, in practical terms, you will, encounter a lot of mathematics because we have to sort of approach it in a formal manner. There is no other option. So we have to do it in a formal and abstract manner. Abstract manner because we are not talking about one particular machine or one particular computer. We are talking about computation in general. So we have to approach it that way. But they have a lot of practical significance and practical this thing, even for people who will not be in theory at all in later on. I know that how many of you will keep on researching in theory in future. Maybe not many, okay, but even for others, knowing the basics theory of computation is very important in all in many aspects, whatever you do later on. Okay, the theorems are widely but not. By the way, this has another implication. These are widely but not universally interpreted as showing that Hilbert, you know, was a famous mathematician in the early 20th century. Hilbert's program to find he wanted to find the complete and consistent set of axioms for all mathematics. Now, most people believe now that this is going to be impossible. As a matter of fact, there is a series of books that was this thing by Bourbaki, which was trying to axiomatize the whole of mathematics. It went to some extent, to quite a bit of extent, and then it was sort of discontinued. Okay. Now we have talked about decidability. Let us talk quickly about unsolvability and undecidability. There is the impossibility of solving a given problem exactly by prescribed means. That is unsolvable or undecidable. We are sort of use it as a synonyms. So there are some problems for which there is a non-existence of an algorithm or the impossibility of proving or disproving a statement within a formal system. That is unsolvability. It is not that the algorithm is presently unknown. The point is that there will be no algorithm. Okay. The non-existence of an algorithm for settling a given problem is often referred to as unsolvability of the problem. Okay, and as you know, you must have done this in flat. For example, the halting problem is unsolvable. Okay, we know this. The notion of an algorithm has to be, but before you can say that this thing is unsolvable, the notion of an algorithm has to also to be formalized. And in any case, we will need to formalize this in this entire course in order to show that some problems is undecidable. The undecidability of a problem means that an algorithm is impossible in principle. Not only that no algorithm is presently known. Now, there are various ways to formalize the notion of an algorithm, and we will see three of them. Three of them will be considered in this course, namely the general recursive functions, lambda calculus, and Turing machines. You are sort of familiar with Turing machines. You will come across general recursive functions and lambda calculus here. There are a few others also they tried. Now, and you can, if a problem is unsolvable, it is going to be unsolvable in any meaningful formalization of algorithms, whether it is functions, the general recursive functions, or lambda calculus, or Turing machines, they are going to be unsolvable in any of them. The most common among such formalizations is a Turing machine. So we will come across Turing machines all the time in this course. So it is to be emphasized, however, that all suggested formalizations have turned out to be equivalent. Okay. It is not only that we are not talking about any particular computer or family of computers, we are talking about computers and computation in general. And we are formalizing it. And not only that, we are not talking about only one particular formalization. There may have been different ways of formalizing it, and it is independent. When we talk about an undecidable problem, this is independent of the formalization. So most probably, or almost certainly, that this undecidability is a property of that problem, not the formalization of algorithm that we may be using. Okay. Consider any such formalization. For any algorithm A and any input word X of A, there are two possibilities. Either A halts with X, this is the halting problem we are talking about. That is the terminating computation result when A is applied to X, or A does not halt with X. In the latter case, one says that A loops with X. The halting problem consists of deciding for an arbitrary pair AX whether A halts or loops with X. This is a well-known undecidable problem. Then we undecidable problems are problems that you cannot solve. And then there are millions of problems which you can solve. And then there are some problems which are called semi-decidable. This is a property of a theory or logical system weaker than decidability, that is semi-decidability. A theory is semi-decidable if there is effective method which, given an arbitrary formula, will always tell correctly when the formula is in the theory, but may give either a negative answer or no answer at all when the formula is not in the theory. That means if something is true, you ask me to prove it, I can prove it. But if that is not in the theory, the algorithm, whether it will halt or not, etc., I mean, this is not known. So these are semi-decidable problems. A logical system is semi-decidable if there is an effective method for generating theorems, and only theorems, such that every theorem will eventually be generated. This is different from decidability because in a semi-decidable system, there will be no effective procedure for checking that a formula is not a theorem. So we can generate that theorem, eventually generate that theorem, if it is indeed a theorem. But if it is not a theorem, what will happen is unknown. So this is a semi-decidable problem. For example, the set of logical validities V of first order logic is semi-decidable, but not decidable. In this case, it is because there is no effective method for determining for an arbitrary formula A whether A is not in V. Similarly, the set of logical consequences of any recursively enumerable set of first order axiom is semi-decidable. Now, I just mentioned general recursive function. Historically, in 1933, Kurt Gödel with Herbrand, they created a formal definition of a class called general recursive functions. The class of general recursive functions is the smallest class of functions, probably with more than one argument, which includes all constant functions, projections, successor functions, and which is closed under function composition, recursion, and minimization. That is a general recursive function. I mean, I mentioned this because this is another important way to formalize algorithms. Another one is Church's lambda calculus. In 1936, Alonzo Church created a method for defining function called lambda calculus. Basically this is where you just apply functions, and functions are lambda expressions in lambda calculus. Once again, we will see it very briefly in this course. So within lambda calculus, he defined an encoding of natural numbers called the Church numerals. A function on the natural numbers is called lambda computable if the corresponding function on the Church numerals can be represented by a term of lambda calculus. Okay. So we will look at this later on in the course. By the way, the language Lisp, which is one of the earliest languages, and once again recently Lisp is becoming very trendy, as you might know. This is based on lambda calculus purely. The third way of formalizing algorithms is through Turing machine. Also in 1936, you can see that all these things are exciting things in theory of computation. The basic things happened in the 1930s. Anyway, before learning of Church's work, Alan Turing created a theoretical model for a machine, now called a Turing machine, that could carry out calculations from inputs by manipulating symbols on a tape. Given a suitable encoding of the natural numbers as sequences of symbols, a function on the natural numbers is called Turing computable if some Turing machine computes the corresponding function on encoded natural numbers. So these are three. There are actually others. We have talked about the three main ones: general recursive functions, lambda calculus, and Turing machines. Okay? And it was found that these three actually are in some sense equivalent, and that is Church's thesis. Church and Turing proved that these three formally defined classes of computable functions coincide. That means a function is lambda computable if and only if it is Turing computable and if and only if it is general recursive. This has led mathematicians and computer scientists to believe that the concept of computability is accurately characterized by these three equivalent processes. Other formal attempts to characterize computability, like combinators, etc., have subsequently strengthened this belief. So, this thesis is the following, that the models of computation that we have sort of created indeed captures what we can compute or what we cannot compute. Under the, I mean, condition, of course, that it has to be theoretically at least physically realizable, etc., etc., and finite number of components, etc. So, under those assumptions, so whatever model of computation we have, whether it is Turing machine or general recursive functions or lambda calculus or others, they actually all come out to be equivalent. So maybe this computability, decidability, semi-decidability, etc., that we talk about, these are, so far as the formalization of the computation process is concerned, we have possibly done a fair job, and whatever computability, decidability, semi-decidability, etc., we talk about have more to do with the problems and the systems rather than the on the computer side or the algorithm side. Okay, that is Church's thesis, and this is what we believe. Okay. There is another aspect of this theory of computation that we will also discuss at the end, that has to do with resources required for solvable problems. One thing that we show that some problems are undecidable, some problems are semi-decidable, some problems are decidable. Now let us talk only about solvable problems. And in solvable problems, there is a question of the what kind of resources it takes, and the two main resources we talk about are time and space. A problem is regarded as inherently difficult if its solution requires significant resources. Okay. For example, you know that we have already known about the complexity of algorithms, O notation, big O, small o, etc., and omega. So these notations, you are already familiar with these, and you have also heard about NP complete problems. So this is sort of a bit more of this in an abstract way, and we talk about both time and space complexity. So a computational complexity focuses on classifying computation problems according to their resource usage and relating these classes to each other. A computation problem is okay, sorry, I cannot read this part. Is, so, what is the time and what is the space required for this? Okay, and and then we divide these problems into complexity classes. Okay, a complexity class is a set of problem of related complexity. Simpler complexity classes are defined by the following factors, which is the type of computational problem. The most commonly used problems are decision problems. However, complexity classes can be defined based on function problems, counting problems, optimization problems, anything. Then we have to mention the model of computation, because, and this is important, previously we say that say some problem is undecidable. We say that some problem is undecidable and leave it at that. We do not say that this is undecidable in Turing machines, because we know that in all models this undecidability concept will remain the same. That is the Church's thesis. But that is not the case for complexity classes. The complexity may depend on the kind of model that you are using. For example, the most common model of computation is the deterministic Turing machine, which is what we will be using mostly. But many complexity classes are based on non-deterministic Turing machines, Boolean circuits, quantum Turing machines, monotone circuits. There are many things. So we will mostly be this thing in deterministic Turing machines and other things. The resource that is being bounded and the function which represents the bound. But bounding the computation time above by some concrete function Fn often yields complexity class that depend on the chosen machine model. For example, the language XX such that X is any binary string. This can be solved in linear time on a multi-tape Turing machine, but necessarily requires quadratic time in the model of a single tape Turing machine. So, if you when you put some problem in some complexity class, you have to specify which computation model that or machine model that you are using. I will just give one example. Let us say complexity classes by space requirement. Just as you talk about time, say order n complexity or order n square or n log n or whatever you call it. Similarly, space also you can the space requirement, and you can bound it by some function. So the complexity classes, as you see here, are say this space Fn, L, P space, X space, that is the exponential space. The models over here are all deterministic Turing machines. Similarly, you can have another table with non-deterministic Turing machines for the same specific space complexity classes. So space may be order Fn, space may be order log n, space may be order polynomial of n, that is the P space, and space may be order 2 to the power polynomial of n, that is the order, that exponential space. Okay, so this is just an example of one example of different complexity classes, and as I mentioned, that you have to mention the model of computation over here, because a particular same problem may fall in different complexity classes depending on the machine model. Okay, I'll just stop here for 1 minute. Any question up to now? So this is what we will be covering in our theory of computation course, mostly. Okay. All right. Lastly, we will talk about what will not, let me just mention that what will not be discussed, okay? So, the universe is, for example, some questions which may come up, so, but we are not going to discuss this. Is the universe equivalent to a Turing machine? The implication being that if the universe is equivalent to a Turing machine, computing non-recursive functions is physically impossible. So it will not be physically realizable. But we are not going to answer this question or even address it. This has been termed as Strong's Church-Turing thesis or Church-Turing-Deutsch principle, and is a foundation of digital physics. Okay, but we are not going to go into this. Maybe it is, or maybe it is not. Okay, we are not wedded to any one of these topics. The universe is not equivalent to a Turing machine. That is, the laws of physics are not Turing computable. But incomputable physical events are not harnessable. That means you cannot harness incomputable physical events, so that you cannot have, for the construction of a hypercomputer, for example, a universe in which physics involves random real numbers as opposed to computable reals would fall into this category. Random numbers, we sort of use pseudo random numbers in our programming and sort of pretend that this is random because we look at its properties, etc. And this is good enough for our simulation purpose. Usually, in simulation, you require to generate random numbers. But really random numbers, you do not have any computer to generate really random numbers. It is not possible. But supposing it is possible, you use some new atomic decay or something to generate real random numbers and harness it in some way. So this is an example of a problem which falls in that category. Another this thing is that the universe is a hypercomputer. That is another theory, and it is possible to build physical devices to harness this property and calculate non-recursive functions. What we said is undecidable, but if we had a hypercomputer, maybe we could decide it. But these hypercomputers have to be very special. They are not just bigger computers. No, not at all. So they are going to utilize completely different physics. So, and actually be able to do computation. We do not know, we do not have such things, but there are speculation that maybe it is possible. So, for example, it is an open question whether all quantum mechanical events are Turing computable. Although it is noted that rigorous models such as quantum Turing machines are equivalent to deterministic Turing machines that have been proved. So they are not necessarily efficiently equivalent. Anyway, John Lucas and Roger Penrose, two famous scientists, have suggested that the human mind might be result of some kind of quantum mechanically enhanced non-algorithmic computation. But anyway, as I said, that even beyond the theory of computation, there are all kinds of interesting things to discuss, but we will not be discussing those in our class. So, is it okay? Once again, is there any question? So, what I have attempted to do in these three classes is basically give you an overview of the entire course. Okay. And I mean, I wish I could get you in a class, but the situation is such that we cannot do this. We have to do this in this distant fashion. And so, what we will do is that we will have a small test in the next class, that is on Monday. So, just a minute, sorry. Yes. Oh, yeah. From 12 to 12:30. Acha. And let us say from 12 to 12:30. Now, and I'll tell you what the naturally that test will be about, whatever we discussed in these three classes, and I'll tell you what the this thing will be. Two of them will just you do the simplest of things using the language of first order logic, so that you become very easy with that language. That was one problem. Another is just Pinot's arithmetic, one problem. So these are two a small problem. I mean, I'm telling you all this so that you can get prepared. Nothing much to get prepared about these two. It is the third one where I'm telling you what I'll ask, and you can be prepared about it. What I want you to do is summarize what this course is all about. That is what we have been discussing. Okay. But it has to be in your own words. And it has to be small, let us say within 100 words. So you may think about it in the meanwhile. We will ask you in the exam on Monday, that test on Monday. But I am telling you very frankly what I will ask. Okay? So that it gets into your head, okay, so this is, you see, I understand that many of you will not be doing theory later on. Okay. But what is it? But you must take, since you have to go through this course, and we all have to go through this course because it is in the curriculum and there is a certain syllabus, etc. So we must be able to derive something out of it, even a little bit, even if I go in some other direction. Okay. So what I have done is I have tried to summarize what we have, what we will be discussing in this course. So please look into it and summarize it yourself so that you know what will be discussed later on in the course. So this one you will, so that you can remember this. Is it all right? Any final comment? And from the class next to that, that means from Tuesday onward, next Tuesday onwards, Dr. Sudeshna Kole would be taking these lectures, although I would be available in the course somewhere by her side, if this thing. Okay? Any
Sir?
other? Yeah, yeah.
Yeah, like this, will this test be like handwritten or do we have to type in the computer?
Type in the computer, possibly, because you'll have to send it. I mean, they are asking whether it is be handwritten or type in the computer. It could be handwritten. Oh, it could be handwritten and then you can send the image.
Okay.
Okay? All right. Yeah. But there will be a time limit. Okay? Yeah. Any other question?
Sir, on what platform will the exam be held?
Whatever platform you are having. I mean, they're asking, let me, this thing. Okay, let me do one thing. Let me hand this over to Dr. Kole. So she will tell you, she will be able to answer these questions. Okay?
Hello? Can you hear me?
Yes.
Okay, so the test will be from 12 to 12:30 on Monday, and I'll be sending you an email with all the instructions. You can just write down the answers on your text on your books, exercise books, and take photographs of that and send it to us. Photographs or scans, whatever you can do, and send it to us. We will give you an email ID of a TA. I'll send you the email. So there are two options. We will prefer if you can upload these photos as a zip file onto Moodle, or if you cannot access Moodle at all, then onto your Microsoft Teams. There is we will be setting up the assignment over there as well. And in the worst case, if you cannot do either of them, you just send over these files, the photographs that you have taken, you send them over by email to this TA. We will give you a specific email address. You send it over to the email address. Okay, and during that time, is there anybody who is attending right now who has issues with the internet? Is there anyone, or is it fine for
Like,
you to?
like the only problem which we might face is that during the test, suddenly if the electricity is cut at our home, then we don't have net as such.
Okay.
Like the only
So
backup is sort of mobile data, so we might have to send by mail. In that case, the pics.
Yes, yes. So that's why we have kept the option of sending by email. This is a blanket rule throughout the course. Even if you have timed tests like on Monday, you can always, within 15 minutes of ending the test, you can always send in your answers through answers by email to the assigned TA. Okay, so you don't have to worry about if your Moodle is not working or if you cannot upload. You don't have to worry about that. You can just send it over by email. Okay, are the logistics clear now? Anybody has any questions? Okay,
So
then
it's
that,
clear.
yes?
No, I just said it's clear. Thank you.
Okay. So then we'll end the class today. I'll send you a detailed email about the exam on Monday. Yeah, and from Tuesday onwards, I will be taking the lectures. Okay, thank you.